So where in the world does this equation come from? So this equation is referring to what the force would be. So this is the force, the M just stands for magnetic, so it's caused by the magnetic field, on a particular wire. And that particular wire has a current, okay? So that current is designated as I. The length of the wire, or the length of the piece of the wire that you're interested in, is just L, so capital L. This is the magnetic field kind of strength within here. And then this right here, so this theta, is just the angle in between, okay? So where the current is traveling. So this is the conventional current, so those are the positive side. And so that conventional current, in which direction it's traveling relative to the magnetic field. So you can find the angle in between there, and then you have to take the sine of this. Now, this comes from the concept that you have actually already hopefully learned, and I'll assume, okay, that you have watched, okay, and understand what is the force on a charge when it is moving through a magnetic field. And I'll put up a link up above there, okay, so if you have forgotten that. So let's break this down and let's see how exactly this works. So if we have some piece of a wire, so it doesn't matter how long this piece of wire is, or maybe you're only interested in a certain portion of the wire. So let's say maybe so from here all the way down to here. So I'm going to call this, so this particular, okay, length, okay, so this is going to be our L. All right, so we're interested in that piece of the wire overall. Now, if you go back and you start thinking about a charge, so if a charge was moving, so that particular charge, so let's say this is my charge Q, and if it was moving at a certain velocity, so here is maybe the velocity that we have in here, so it's moving to the right or whichever direction, okay, that you want it to move, and it is in a presence of a magnetic field. So now let's say that magnetic field, okay, so let's say it's pointing, okay, maybe something like this. I'm going to just duplicate it so that it creates this field for us, kind of arrows pointing in. So this would have been my magnetic field. Okay, so this is the direction of it. Now, of course, so this is going to have a certain magnitude. So for this that we have, so that would have been our B. Now, the angle in between here, so notice that the angle that you would be interested in would have been the angle right here. Okay, so between the actual charge, which it's moving at a certain velocity, and then your magnetic field. And that particular result came down to that the force on this particular charge was equal to, so at least the magnitude of the force is equal to just the charge itself, and then multiplied by the speed that it is moving, so the magnitude of the speed, the strength of the magnetic field, and then it was sine, and then the angle in between. So now if you want to replicate this and then relate it back to this equation that we have within here, so because clearly we see an I, which is the current, and this is the length of the wire or the piece of the wire you're interested in. So it doesn't look exactly like this, although this B that we have in here and then the sine of the angle is indeed identical. So where does that come from? So let me kind of take this in and start to clean it up a little bit. Now, I'm going to, just for convenience, okay, so remove some of this magnetic field so that it's not causing us any issues, okay, so within here. So let me remove that. And now I am interested in this piece of the wire. All right, so how am I going to relate it back? So please don't forget that your current that is flowing through a wire, so we're going to assume that the current is flowing in this direction. So that is my current. Well, the current is defined as the amount of charge which passes by a certain unit of time, right? So that is how the current has been defined. So if that is the case, well, notice you're seeing this Q in here, which is the charge itself. And now what you're going to take a look at is the following. That if you wanted to break this down and you have charges and these charges are passing through in here, so those charges are passing along, which are creating this particular current that we have, then what you're going to find is this, that, oh, okay, well, so within here, so this is my charge Q, okay, so my speed, okay, so within here, well, what is speed? Well, speed is whatever distance that you have. So the distance that these charges are covering in this piece of wire is L. and that speed would be just L divided by delta T. So if you plug that in for speed, what you're going to get is you're going to get Q multiplied by L divided by delta T and multiplied by B sine of the angle. So now, if you connect back, well, again, notice that Q divided by, so the delta T, so this is Q divided by delta T, well, this is nothing else but simply the current. And there you have it. So you have your equation, and so this would have been your current that is passing through. B is going to just stay the same, and then you have sine of the angle. So that's exactly where this formula has come from. So once you understand how charges are moving and what the force is on those charges, then you can definitely derive this equation. Now, of course, this is just a magnitude, so you would need a direction, and then in order to find the direction, you would use the right-hand rule. So the right-hand rule is exactly the same thing. The only nice thing is that we're always talking about the conventional current in here. So that conventional current, we're not going to be worrying about the electrons, okay, that are flowing, because electrons are actually flowing in the opposite direction. But you always take the conventional current, which is passing through a wire. And for the right-hand rule, you know, you can definitely kind of go back. Okay, I'll put up a link up above there. So if you wanted to take a look at this. Now, let's relate this back to an example and see how this becomes now pretty useful. Now let's try to apply the formula itself to an example. So here is the DC motor. Okay, it's back. If you like the whole explanation on the DC motor, how it works, okay, and you know what happens in terms of its rotation, I'll put up a link up above there. So when you have a magnetic field, so our magnetic field here, so since we have a north and a south, so our magnetic field is going to be pointing in this direction. We have some kind of a wire loop, okay, so within here, so within your DC motor, and we're going to shoot a current, okay, so through this. Now, if you want to have a more visual instead of just a basic schematic, so here it is, okay, so here's the reference there at the bottom. So this is kind of how it looks like, and this is exactly what I explained in that video that I was pointing out. And what we want to be able to do is, in this example, is to apply the formula and find out actually what the force would be. So not just the direction and understand how it is moving and it forces the loop to move, and then eventually how those motors work. We want to be able to find out exactly what the force would be. And in this example, what we're going to do is we're going to take, okay, so one of these wires, okay, so this has kind of 4 strips as you're going through, but we're going to just take this one right here, and we want to be able to find out what the force will be. And then I'll mention the direction as well, but of course, you know, the direction is going to be something that you should be familiar with. All right, so here it is. So this is kind of how it would look like, and here are all of the numbers that we're going to be working with. And of course, you know, you would need to know what the current is. You would need to know what the actual length of the wire that you're interested in is. You would need to know what the magnetic field strength is as well. So here it is, kind of in a smaller format. So again, so we're interested in just this piece. And if you translate this back into these 3 dimensions, you have your current, which is flowing through. And in that particular instant, because it is an instant, okay, so as it will start to move, so it will change. But in this particular instance, what we want to know is what is going to be the force on this wire. So this wire has a certain length. So here is our length. The actual magnetic field has a certain strength. Okay, so here is the strength. The angle, at least in this instant, is 90 degrees because of the fact that this is, okay, your magnetic field, and then your current is perpendicular. So it's flowing perpendicular at this instant. And then here is your current, okay, so there's nothing big. So none of these are going to be very big for us. Now, one thing that you'll notice is you might say, oh, well, this is my magnetic field, and it's 150 G, and I haven't seen a G before within here. So you will recall that magnetic field are measured in Tesla, but Tesla is a rather big unit. And sometimes what we will do is we're going to use a little bit more convenient unit, okay, if it's something smaller. But 1 Tesla is actually equal to 10,000, okay, and then the G stands for Gauss, another scientist, okay, so that has worked, okay, in this. And if you are a student who's going to be continuing on after foundational physics, you are going to hear of Gauss probably quite a bit on electromagnetism side. So that is nothing, okay, but a unit conversion. So if you want, you can certainly convert this back in, and this is going to be 0.015 Tesla. So if you do that unit conversion, I'll leave that unit conversion up to you. We should probably switch all of these units to metric standard units, because when we're calculating the force and we're substituting everything back in, we should have metric standard units so that we have this measured out in newtons. That's exactly what we want to be able to do. So I'm going to change all of these to metric standard units. So 1.8 centimeters, so that's going to be 0.018 meters. That's what we have there. So the angle just stays as it is. It's 90 degrees. And then 15 milliamps. So that's going to be 0.015 amps, right? So that's what we have. We're moving the decimal place just 3 over. So substituting all of these pieces in, what we're finding out is the force on this particular piece as the current is going to be flowing through this. So not very difficult. You can substitute all of these numbers in here. Notice that sine of 90, so as you're going through, is just going to be equal to 1. So this is a very simple calculation. So let me do that and plug the numbers back in here. There you have it. Okay, so it's a very small amount of force. Now I have just thrown these numbers arbitrarily. You can certainly dig up, okay, information if you're really interested about motors in general. But my concept and idea was to take the equation and then just show you that, okay, so it's not that difficult to be able to find out what these forces are. And now the question always arises, okay, so in which direction would this be? And this, you would have to use your right-hand rule. Okay, so as you're going through, and I encourage you to do that right-hand rule. So you're going to take, so in this case, notice that what you have is you have your current, okay, so which is passing through, you have your magnetic field, and again, remember, you're going to go from the current, okay, so and that current that you have, so this is the direction of the current, because that's the direction in which the charge is flowing, conventional charge. And then here is your magnetic field. So if you do that, you'll notice that in this case, the way that I've drawn this, if you use your right-hand rule, it's going to be into the page. And so on this diagram, so as you're going through, so if you would do that within there, that means that the force which is present here would actually be downwards. Okay, so that's where the force is, and this is your strength of that force. So don't forget, you will use the right-hand rule in order to find out in which direction, okay, that force is present. And I would encourage you, if this is the same current, the same length, you will notice that within here, if you would be trying to now take a look in this would have been pushing upwards, okay, so that force would have been upwards, and that's why this starts to rotate, right? So and then it starts to move as you're progressing through that motor. But now you have the skill, once you've used the formulas, to find out what the actual force magnitude is, because you were familiar with the direction. All right, so that is it for this video. Thanks for watching. We'll see you in a future one. Bye, everybody.